Hello, my name is Eun Sun. I'm a PhD student at Seoul National University. I'll be presenting a work titled Self-Supervised Domain Adaptation for Visual Navigation with Global Map Consistency. In this paper, we investigate the scenario where the pre-trained navigation agent in a noiseless simulator needs to be transferred to a new environment where the agent's actuator is noisy and the odometry measurement is also erroneous. As a solution, we introduced a simple and generic self-supervised learning method for noise-robust visual navigation. So here's the overview of our approach. We employ the modular approach that separates the observation space and the action space as shown in the figure. The observation module transfers the sensor perception into the domain-agnostic intermediate representation, which are the predicted global map and the estimated pose. And a subsequent policy module deduces the agent action from the intermediate representation. Then given corrupted measurements from the actuation and odometry noise, it suffices to fine-tune the observation module only to produce the stable intermediate representation. Yet, adapting the observation module requires either ground truth poses or explicit noise models, which are not available in the realistic setup. So we formulate a self-supervised learning task where the agent is encouraged to generate consistent global maps at different time steps. To implement this self-supervised learning task efficiently, we deliberately design overlapping trajectories by driving an embodied agent in round trips as shown in the figure. First, the agent navigates the new environment for a designated number of steps and turns 180 degrees. During this forward path, the agent generates a reference global map and a predicted pose from the observation and odometry reading from time 1 to TR. And we drive the agent to execute the previous action sequence in reverse. On its way back, the agent generates a new map. The same global coordinate is shared across all global maps, and the agent continues incremental pose estimation using the full odometry. At each reverse step, a new global map and the pose estimation are predicted. Finally, our self-supervised task imposes the consistency between the reference map and the newly predicted global map to fine-tune the mapping module under the new environment. We compare the estimated map at every step during the backward path, providing a reach set for loss computations. We also suggest a data augmentation method. While the vanilla formulation utilized the bisections of round-trip trajectories, the consistency can be enforced for any subsets of trajectories with overlapping observations. Given a trajectory, data can be augmented by randomly sampling 3 time steps in a chronological order: the initial time t1, the turn time t0, and the end time t2. In the right side of the figure, you can see few example trajectories augmented from the original trajectory. Here's the qualitative result. The first row and the second row each shows the generated map and the trajectory from all agents executing the same sequence of actions. We compared our model with 3 baselines. All baselines begin with the model pre-trained in a noiseless simulator with ground truth information. No adaptation is the pre-trained model deployed in a new noisy environment without any adaptation. It reflects the performance degradation due to the domain gap and sets the lower bound of adaptation. We also compare our method to the domain randomization, as it is a learning approach widely used for domain adaptation. The model is randomly trained for the various combinations of noises with ground truth supervision. GT Supervised is the model fine-tuned with the ground truth supervision in the new environment, so then it serves as the upper bound of the performance for our adaptation model. We can see that our agent better aligns with the ground truth compared to no adaptation agent or domain randomization agent. In conclusion, we introduce a simple self-supervised task for robust visual navigation amidst actuation and sensor noise. We also demonstrate that the suggested formulation enhances the localization, mapping, and the final task performance of an embodied agent. Finally, in the paper, we provide an additional experiment which shows that the proposed method is applicable for test time adaptation, indicating the potential applicability for real-world deployment. Thank you for listening.